Hello, my name is Taeun He, a master's student in artificial intelligence at DGIST. Today I will be presenting a pace-preserving gray box model for robust sonar signal separation. First, let me explain the purpose of this study. This research focuses on using deep learning models to restore n original signals from n mixed signals received through the passive sonar. The separate signals are then classified using a classification model to identify the type of each signal. The first model developed for this purpose has the structure shown in the diagram. Let me explain the overall structure of the model. A mixed signal generated by combined n original signals and fed to the encoder as input. This signal passes through the 1D convolution and parallel layers, producing a 2D feature map of size n by L, and this feature map then becomes the input for the separation process. To convert the feature map into a 3D tensor, it is divided into chunks overlapped by half and stacked to form a 3D tensor. This 3D tensor undergoes inter and intra-chunk processing with overlapping. The resulting output is then passes through the model's decoder, where it is reconstructed into the individual signals as output. The results are as follows. As you can see, the proposed model significantly outperforms the traditional signal separation algorithms such as ICA and JADE, achieving much higher performance metrics. During the course of our research, our team identified a crucial issue. Traditionally, AI models are often considered black box models, which makes it difficult to interpret their internal working. While the inputs and outputs are clearly observable, understanding the intermediate processes and specifically identifying the features that the model focuses on to perform signal separations proved to be a highly complex challenge. In the case of our previously proposed M1MD deep neural model, which is structured as a recurrent neural network, information is continuously updated and propagated over time. As a result, the output of the specific time point depends on all processing input. This creates a problem where it is difficult to precisely determine which combinations or pure inputs contributed to a specific output at a given time. To address this issue, we propose a new methodology to overcome these challenges and enhance the interoperability of the model. And we have been exploring various methodologies for separating mixed signals in underwater environments. Traditionally, mixed signals received through the passive sonar were separated by analyzing the characteristics of each signal. However, these approaches relies on the model to automatically learn and extract features, which does not especially reveal the features crucial for signal separation. In other words, these methods exhibit the black box nature of AI models, making it difficult to identify which features play to significantly role. To address this issue, our team developed the cycle ATT TASNA model, which combines the TASNA model with the self-attention mechanisms and utilizes cycle consistency. This model performs knowledge-based signal separations and particularly focusing on tonal signals concentrated at specific frequencies, such as those found in the ship signals. Marine life sounds or general noises without tonal signals are categorized as anonymous signals and processed separately. The model also provides step-by-step visualizations of the process from tonal signals, descriptions to final separations, allowing for a clearly understanding of how the model operates. Building on this, our current research focuses on developing an interpretable AI model that is robust to noise in underwater environments that capable of separating signals certainly on specific frequencies. Particularly tonal signals, and this approach not only enhance performance, but also provides greater insight into the model mechanisms. The cycle ATT TASNA model is designed to effectively separate underwater acoustic signals by learning key features from the input. First, the model extracts important features using 1D convolutions, which captures essentially patterns in the signal while the parallel activation enhances representation. Next, the transformer layer with a self-attention mechanism selectively focuses on crucial time frequency regions and isolating meaningful tonal signals while suppressing noises. Finally, the separated signals are reconstructed into the original format through transport 1D convolutions, making them easy to use. This structure ensures robust and efficient signal separation while maintaining the interoperability. Now let me show you the visualization results of how the model focuses on specific areas during the signal separation process using the self-attention mechanism. The first image highlights the model focusing on specific time and frequency regions. Bright areas indicate the attention, showing the ability to identify the purchased key signals. And also the second images also determine attentions on different times and frequency regions. The bright spots confirm the model in pays on essential information, surprising 11 parts for efficient signal separation. These results showcase how the cycle-ATT Tasman model not only separates signals but also offer interpretability and enhancing reliability on significantly advanced in signal processing. The term cycle in cycle-ATT Tasman refers to the integrations of cycle consistency as a loss function. This methodology ensures that the mixed signals after separation and resynthesis matches the original input by compressing the original and resynthesis signals. The model achieves consistency and accuracy. This approach offers several advantages. The first is it presents the model for copying the input, reducing overfitting. And the second is it ensures transformations consistency, providing stable results. And the last is it ensures the separated signals and mutually exclusive and collectively enhanced. And by minimizing information loss and promoting distinct and comprehensive separation, cycle consistency enhances the reliability and interpretability of the cycle-ATT Tasman model. The MDDPRM model and cycle-ATT Tasman models differ significantly in their processing methods and interpretability. The MDDPRM usually uses an RNA-based sequential structures where outputs depends on previous inputs. This makes it difficult to trace which inputs influence a specific output, resulting in a black box model that lacks interpretability and cannot provide insights into the decision-making process. In contrast, cycle-ATT Tasman employs transformer structures with a self-attention mechanism, allowing it to focus on specific time frequency regions. And self-attention weights can be visualized, making the model more interpretability as a gray box model. Additionally, the incorporation of cycle consistency ensures that separated signals retain crucial information from the original mixed signals while preventing overfitting and maintaining mutual exclusivity. The dataset was structured as follows. It consists of signals from 10 different types of vessels. Each signals were divided into 5-second segments and then split into train, validation, and test set. To augment the data, the signals were further divided into the 1-second segments with a 0.2-second overlap between them. And these are the results are as follows. The left part is the original signals, and we mixed it, and the middle part is the mixed signals, and the right part is the separate signals, which is the output of the model. And if we look at this as a spectrogram, then we could see the result as like this. But as we could see, we couldn't know the model separate really correctly. So if we see more deeply, we can see the results as like this. As you can see, the performance of the proposed cycle-ATT Tasman model shows a slight decrease compared to the MDDPRM. And the key advantage of the model lies in its improved interpretability. This trade-off highlights the unique strengths of the cycle-ATT Tasman model. Thank you for listening, and if you guys have any question, then be free to contact me as a mail below. Thank you.